Welcome to my next video. This time we'll have a look at a very non-problematic, I would say, standard structure determination with some easy molecule just to give you some more experience in data processing and then structure solution and refinement. In the section below the video, you can see a link to the Zenodo repository where you can download the raw data and play with it in CrysAlis Pro on your own. I'm going to go to the folder right now that you can download, and we'll go for the parameter file. It's a non-complicated molecule. It's one of the reagents that I used during my synthesis recently, but I noticed that it's not in the database and it magically crystallized, forming okay-ish crystals from an oil that I obtained after synthesis. After some time, and I thought, yeah, why not? Let's put it into the database if it's not there. Okay, so tar file. We can already see that it looks like a strong data set. It probably looks single, right? We go here, we do ping hunting. We can see some data from my previous processing, but let's ignore it. Let's do it straight from the beginning. Ping hunting. I will now pause recording and I will resume once it's done, and it will take some time. Pig hunting that's how it's called in the CrysAlis language. The Brooker people would probably call it something like pig harvesting, I think. But I'm totally a Rigaku person. I'm a loyal customer. Okay, I'm going to pause it right now. And it's done now. Okay, so we can do in cell finding. It finds a cell, very nice indexing, almost 98%. And we don't really have other choice. So any cell can be reduced to or represented as triclinic primitive cell. That's why there will be always one cell like that with value of 0. And our value here is what we look at, and it's very close to 0. So that's the correct cell. If there was another cell which has a value, for example, 0.8, we would still choose this cell because then this value is very close to 0 and 0.8 is quite far from 0. So this cell is probably the correct one. Okay, and we go to the Evalt Explorer and we see that indeed in all of the directions it looks all very, very nice. Okay, so let's do integration. We go to Start Stop, data reduction with options, next, next. We clear data from previous integration that was done. Yeah, we leave it all here like it. I usually go for smart background with the, especially with the instrument that I'm using, and with even bad or very good data, I usually go for smart. That's what I was told during training with Rigaku people. Yeah, we can have a look at the formula. I think this formula is almost correct, maybe even completely correct, but we can leave it like this. There's definitely one bromine and some carbon and one nitrogen atom. It estimates Z as almost 4, and indeed for monoclinic P cells, it's either 2 or 4. So 4 is fine. It says that mu is below 4, which is fine. We probably won't need to do any phase indexing to correct for absorption, and multi-scan absorption correction will be completely fine with that, which is nice. Okay, so we set mu and formula and finish. And again, the integration, all of that will take some time, so I will pause right now and resume after it's done. And it's done now. So apply, yeah, P lattice. Yep, very nice. Arint, 2.1%, cool. And here it suggests us that it's centrosymmetric structure. We basically want to look at this e² - 1 parameter. For acentric, it will be, for acentric distribution, it will be around 0.74. For centric, 0.97, and in our case, it's 1-ish. So it's center-symmetric. Now it suggests a solution in 3 different space groups. These are essentially the same, but according to convention, we're going to choose the space group where beta angle is closest to 90 degrees. It's just a convention that we should follow. Crystallography is all about conventions. Apply. Yep. For finish. It's doing some stuff. Okay, our int is now 2%. Let's have a look at our reduction graphs. I'll also go for the rint graph, and you can see that there's like 2 frames where rint is larger than this 0.08. We can probably remove them using filters at the data finalization. So let's remember that we want to apply filter for rint, let's say, higher than 0.08 to cut it here. Okay, we can have a look at the crystal. Crystal is here. It's irregular. We can measure its dimensions more or less. We don't really need to do face centering, face indexing, because we'll do multi-scan, because mu is not terribly large. So we could have a look in this direction, for example, it's 0.02, here it's 0.07, so this dimension would be 0.09, right? So we can measure it like this in 3 different directions, and either note it somewhere, or we can also put it, sorry, not here, description, irregular, clear, light, yellow, and put some values, the ones that we measure, to the minimum, medium, and maximum. We can input it later in OLX2 as well, or even manually in the zip file. Okay, so I'm going to exit right now, and well, let's refinalize it. So I always like to put different names to my files. This is already called WS, my initials, so that's from my previous processing that I did before recording this video, so I will call it WS2, so I know what's going on. Yes, here we want to add filters, so we go for manual filters. It's called rint frame filter, and we want to filter everything that is larger than 0.08. Okay, and we want to trim the data to, yeah, we don't need to click it here, but up to 0.8 angstroms. And I also go for the interactive space group determination. Okay. Yeah, apply. Okay, so our rint at the end is 2.9%, also very nice, I over sigma. Okay, I can close it now and go to the struct folder. And this is our folder with our process data. We open the ins file in OLX2. No, please, no updates, Mr. Alex. Okay, we go to work. I'm going to use shellxt for solution, and let's solve it. Yay, looks very nice. We can do Ctrl R or click refine here. For refine, I will use least squares with shellxl. Ctrl R, we refine. We can already see that it found most of hydrogen atoms. We can also input anis or click here to perform an isotropic refinement. Okay, and we can do hadd to add hydrogen atoms, or another way to do that is to go to here, add hydrogens. But I always try to use command set. Command set is much faster. Okay, Ctrl R. Okay, right. I will actually delete hydrogen atoms now, and first name the atoms, because later the hydrogen atoms will also be named according to the naming we are putting to normal atoms, let's say. So this is bromine, Br1, and name N1, and all the other carbon atoms I will name using this naming option. Start with 1 carbon. It's not really necessary to name that, but firstly, when you leave these labels that are created by Olex, you'll get an alert in G-level alert, but still an alert in CheckSif, and also some reviewers might not like it. Another reason why you should generally do that is that because, especially if you have disorder, then it's much easier to work, write restraints and stuff like that when you have very nice numbering scheme. Okay, so I'll do hadd now and Control R to refine it. I can update the formula. Let's do more cycles. Let's do weighing scheme, acta, so it reads the CIF file, and let's refine it. Okay, looks very nice. But one thing you should always do is to have a look at the electron density map. So firstly, you can see that you have some maxima, but they're close to the heaviest element. Bromine is quite heavy, right? It has a lot of electrons, so it's normal. But if you do Control M, you will go to electron density map. So it's not surprising that there is negative electron density, which is indicated by this red grid. Positive electron density would be green grid. It's normal for heavy elements, but we also have negative electron density here, negative difference, which means that there is too many electrons at this point. Another thing that might tell you that something is not okay with the current assignment is if you have a look at the bond lengths. If you have a look at the bond length, this one, Cn, it's actually quite short. It's 1.28. So it's not an amine, it's an imine. There is a double bond in here, and there is no hydrogen. If you do refinement now and go for the electron density map again, we can see that this problem disappeared now. We can update the formula. We can also have a look at nobody reflections. We can have a look at FOPS versus FCalc map. We can see that something is a little bit going down here. And this is related to that it suggests us that there is some extinction. We can correct for that and introduce extinction parameter. Again, refine. The model got better. We can see that there is some extinction. It's definitely, well, it's not a large value, but it's significantly larger than 0 if we have a look at the standard deviation. Refine. Okay. To have a nice CIF file with everything arranged nicely, we can also click sorting, sort. Now it will be in the CIF file like N1, C1, C2, C3, C4, rather than, I don't know, C1, C10, N1, C20, blah, blah, blah. Okay, we go to report now. We are done with our structure refinement, but we want to publish the CIF file, right? So we put submitter details. It's already saved all of my data. So I added crystal. For some reason, it doesn't remember the color, even though we inputted it in CrysAlis. So it was something like, I think, clear, light, yellow. Yes. Preparation details, if we submitting crystal structure together with some manuscript dealing with crystal structure that we described there, we can say as described in the paper or the manuscript or supporting information, right? Crystallization details, here I would say slow crystallization of oil obtained during synthesis over 1 month, something like that. Crystal mounting, yeah, I don't think a lot of people do that. I usually do. So I would say nylon loop in this case. NVH oil. It's a very dense oil. It's essentially like paraton oil, which is also a type of dense oil that is very useful. The trick is that you can't really buy paraton oil anymore, and you can buy NVH oil. So that's what I used. Although I have a small amount of paraton oil that I, well, might have borrowed from someone without their knowledge, but we're not going to talk about it right now. Okay, refine special details. If you had to deal with some disorder, you can describe it here. For example, that you had to split some fragment and refined occupancy, added some restraints, blah, blah, blah. That's all. That's the place where you would describe it. All of this information is inputted here from the CIF-OD file from CrysAlis Pro, so we don't need to do anything. We can press merge CIF. And let's do check CIF. Hopefully it won't take too long. It shouldn't, because our CIF file should be very relatively small. It's a small molecule, not much reflection data as well. So yes, and indeed, hopefully it will open quickly. And we'll see whether we have any problems with the structure. Okay, so here everything's fine. I always have a look at the Z, whether it's really correct, calculated, and the reported one. Yeah, and here there are essentially no problems. Everything's perfect in our structure. No C-level errors, only G-level alerts that are more like information rather than something wrong. So we could basically publish the structure in the database now and be happy, which I already did. Okay, so I hope this video was useful to you. Try to get some practice with CrysAlis, explore some options using the dataset that, as I said, is available free on Zenodo. You can see the link under the video. And please comment if you would like to say something, you have some ideas for new videos, you didn't like something, which might also be good to introduce some improvements in the next videos. Okay, thank you so much. Bye bye.